Question number 3. Some students are asked to use the laboratory 28mm microwave transmitter T and receiver R. So this 28 is the wavelength of the microwaves. The wavelength of the microwaves coming out of transmitter T and being detected by receiver R. To design a demonstration to illustrate the principle of a radar speed measuring device. Alright, figure 3.1, a movable hardboard H, which is a partial reflector of microwaves, is placed in front of the metal sheet M, which is fixed. I presume that M is a good reflector of microwaves. The students expect the detected signal to change between maxima and minima, so that's bright spot to dark spot, not bright spot to bright spot. Maxima and minima intensity when H moves a distance of 7mm towards the receiver. Okay, let's have a think what's going on here. We've got 2 paths to get to the receiver. One is a short path reflecting straight off H to the receiver. Let's call that THR, short path. And then we've got a slightly longer path. We'll call that TMR, and that is the long path. Okay, so we've got a short path, a long path. We've got a path difference, which would be the long path, TMR, subtract the short path, THR, whatever they are. And in order to get the distance, in order to get a maxima and a minima, so I'm going to put that up there, then that path difference has to be half of the wavelength of the wave, which is 28mm. Okay, so far so good, I think. When the detected signal is passed, so whatever the receiver is detecting, and the receiver will be detecting loud spots and quiet spots and loud spots and quiet spots as H is moved in this direction. So when the detected signal from R is passed through an audio amplifier to a loudspeaker, a sound should be heard. So what we would imagine as being constructive, destructive interference as H moves closer to the transmitter and the receiver. Because that happens so quickly, if we pass it through an audio amplifier and a loudspeaker, our ears would detect that sequence of loud spots as a hum, as a frequency, as a sound. They claim that when the sheet is moved at 2.8 meters per second, the frequency heard should be around 200 hertz. You are to evaluate whether their experiment is feasible and whether their conclusions are correct. Oh geez, this sounds tough. Part 1. Explain why the detected signal strength should vary and discuss what factors will determine whether the differences between maxima and minima can be detected. Oh gosh, right. Well, let me brainstorm a few keywords. I'll want to mention path difference, phase, constructive, destructive, superposition, and possibly attenuation, as one of the signals, the short signal, is going to have a higher amplitude possibly than the longer signal, because the longer signal has to make it through H, so that's going to remove some of its amplitude, reflect off M, presume none's going to be lost there, pass through H again, which means it's going to have a little bit of its amplitude lost, and then detected at R, plus that's a longer distance, so the signal will be weaker by the time it gets to R as well. So there's definitely going to be a significant amount of attenuation in the long path compared to the short path. Okay. Well, I will answer this initially. I'll try and answer it the way that the Year 12s currently would probably answer this, by talking about why you get a maxima and why you get a minima, and that would cover the basics. So I'll start my sentence with because H is a partial reflector, there are 2 reflection paths. THR is the short one and TMR is the long one. If the path difference, TMR subtract THR, is a whole number multiple of the wavelength, which is 28mm, then the 2 waves will arrive at R in phase and constructively interfere, producing a maximum intensity in the detected signal detected by R. When the path difference is half lambda, half the wavelength, 1.5 wavelengths, 2.5 wavelengths, 14 millimeters or 42 millimeters, etc., referencing the wavelength given at the start, then the waves arrive at R out of phase to produce a minimum detected intensity. Now, looking at this part of the question, determine whether the difference between maxima and minima can be detected. That all depends on whether the two signals that are arriving at R are similar in their amplitudes. If they are really similar in their amplitudes, then the constructive and destructive interference will be really pronounced. And if the difference between the two amplitudes is quite a lot, so if the longer path difference has a significantly smaller amplitude than the shorter path difference, then the difference between a maxima and minima will be a little bit more difficult to detect. Quite how to fit this into a handful of lines at the bottom of the page so far is going to be pretty tricky, but I'll try my best. The reflected signal THR, which is the shorter path, will have a larger amplitude than TMR, and TMR is the longer path, because of the attenuation caused by the longer path having to pass through H twice. So passing through H once, losing a bit of its amplitude, reflecting off M, passing through H again, losing a bit of its amplitude, finally being detected by R. I suppose you could also mention that because the path is a longer path, there'll be a certain attenuation associated with that too. If the difference in amplitude between the two reflected signals is small, then the two waves will vector sum their displacements to produce clear maxima and minima in superposition. Oh geez, what a hell of a sentence. Let's do the counter-argument. If the difference between the amplitudes of the two reflected signals is large, then the difference between maxima and minima will be less and therefore more difficult to detect when they're in superposition. So what I'm trying to communicate here, and this is hard work to do this, is that if the two signals arrive and they've got similar amplitudes to each other, then that means the process of superposition, constructive, destructive interference will be much more clear-cut. You'll get very clear maxima and very clear minima. But if the two reflected signals arrive at R with significantly different amplitudes to each other, then in the process of superposition, where you have constructive and destructive interference, you're adding two signals where the amplitudes aren't identical, and therefore the difference between maxima and minima will be a little less pronounced and more difficult to detect. But the number of lines that I have to try and communicate these complicated ideas, sort of not really knowing exactly what the mark scheme looks for, you can clearly see that I started to write a little bit wider and a little bit wider as I went down, ran out of lines and kept writing and kept writing. So it'd be interesting to see what the mark scheme awards for this particular question. Part 2, justify the student's prediction of 7 millimeters between maxima and minima and a sound of 200 hertz for a speed of 2.8 meters per second. So they reckon that if you were to move H in this direction at a speed of 2.8 meters per second, so what it says, 2.8 meters per second, then the maxima minima cycle detected by R when put through a speaker would come across like a sound, and that would produce a frequency of 200 hertz, which means 200 loud spots per second. What a nightmare. So let's have a think about this. The prediction of 7 millimeters between maxima and minima. So that 7 millimeters is going to be the difference between M and H. So that distance there is 7 millimeters, and that 7 millimeters is between maximums and minimums, which means that that would be representing half the path difference, because the path difference is HMH, and that would be 7 millimeters and 7 millimeters, which is 14 millimeters would be the path difference. But the distance M and H is just 7 millimeters, which is half of the path difference that we're detecting over here. And for a maxima and minima, the path difference has to be half a wavelength, which in this case would be 0.5 times the wavelength, which was 28 millimeters, which would be 14 millimeters would be our path difference, and the distance m and h between m and h would be half of whatever that path difference was. So half of 14 millimeters is 7 millimeters. All right, try and put that into words. The distance mh is half the path difference. The path difference for a maximum and a minimum is half the wavelength. So the distance mh would be half of half the wavelength, which is half times a half times the wavelength, 28 millimeters, which is 7 millimeters. Phew. So now I want to try and get this 200 hertz, which should be thought of as 200 maximas achieved per second, and I would have to be looking at how the distance between maximas, not maxima and minima, the distance between maximas. So that's not going to be 7 millimeters for a maxima minima. I'm going to be using 14 millimeters because I want to get from a maxima to a minima back to a maxima again. And I want to find out how long it takes, how long it takes in time to get from one maxima to the next maxima at a speed of 2.8 meters per second. I would not be surprised if you get completely lost at this point. So let's call the maximas loud spots. The distance moved by h between two loud spots would be 14 millimeters. The time taken to move this distance at a speed of 2.8 meters per second is distance divided by speed, 14 millimeters divided by 2.8 meters per second, and this would give us 5 milliseconds as the time between two loud spots, which, and I've run out of space, so I'll have to draw a little asterisk and slide all the way down here. Make sure I start writing below the 3. I hope the next question doesn't take up too much space. Which would be the time period between neighboring loud spots. The frequency of loud spots would be 1 over 5 milliseconds, which is 200 hertz, which is what they're after. Geez Louise, that's a tough one.